Hello everyone, my name is Sham Parikh. I'm a student of BSc Chemistry Honours first year. My roll number is 10 and today I'm going to read the chapter Gaseous State written by Dr. S. Kiran and Kavya from the book Modern Approach to Physical Chemistry. Gaseous state. Among the three states of matter, the gaseous state is the simplest one. Gases show maximum uniformity in their behavior, irrespective of their nature. Gaseous state is characterized by the following physical properties. Gases possess capacity of indefinite expansion. They acquire the volume and shape of the container they are filled. Gases are highly compressible. Unlike liquids and solids, gases can be liquefied at low temperatures and high pressure. Gases have very low density and under normal conditions of temperature and pressure, gases intermix spontaneously. This property is called diffusion. Gases exert pressure on the walls of the container. Gases exert pressure equally in all directions. The important measurable properties of gases are mass, volume, pressure, temperature, etc. The behavior of gases can be understood in terms of some relationships between these variables PV, T, and mass. These relationships are called gas laws. Gases which obey the gas laws at all temperature and pressure are called ideal gas, while gases which do not obey these laws at all temperature and pressure are called non-ideal or real gases. We take a quick revision of the gas laws. Gas laws, a review. Number one, Boyle's law, pressure volume relation. This law describes the pressure volume relationship of gases at constant temperature. It was given by Robert Boyle in the year 1662. The law states that at constant temperature, the volume of a given gas, the volume of given mass of a gas is inversely proportional to its pressure. For a given volume V of a gas at pressure P, Boyle's law may be expressed mathematically. V is proportional 1 upon P at constant temperature. PV equals to constant at constant temperature. Let V1 be the volume of a given given mass of a gas at pressure P1 and temperature T. Now if the pressure is changed to P2 at the same temperature, let the volume change to V2. Then according to Boyle's law, P1 V1 equals to P2 V2, or P1 upon P2 equals to V1 upon V2, V2 upon V1. Thus, another statement of Boyle's law is the product of pressure and volume for a given mass of gas at constant temperature is constant. Thus, if the pressure is halved, the volume is doubled of its initial value, and if the pressure is doubled, the volume is halved. Number 2, Charles' law, volume temperature relations. This law gives the relationship between volume and temperature of a gas at constant pressure for a fixed amount of gas. It was given in 1787 by a French chemist, Jacques Charles, and was further developed by Joseph Gay-Lussac in 1802. Charles' law states that at constant pressure, the volume of a given mass of a gas increases or decreases by 1 upon 273 of its volume at 0 degree for each 1 degree rise or fall in temperature. If V0 is the volume of a gas at 0 degree and V1 the volume of gas at 1 degree Celsius, then according to Charles' law, V1 equal to V0 plus V0 upon 273, which implies V0 in bracket 1 plus 1 upon 273. If Vt the volume of gas at T degree temperature, then Charles' law may be expressed mathematically as Vt equals to V0 plus V0 upon 273 into T, which implies V0 in bracket 1 plus T upon 273. Absolute scale of temperature. By similar calculations, it can be shown that decrease of temperature results in the decrease in volume of gas. The volume of the gas below 0 degree will be less than V0, and ultimately the volume should become 0 at minus 273 degrees Celsius. At temperature minus 273 degrees Celsius, volume V equal to V0 in bracket 1 minus 273 upon 273, which equals to 0. This is graphically shown in figure 1. Thus, minus 273 degrees Celsius is the lowest possible temperature at which gas is supposed to occupy zero volume, that is, the gas ceases to exist. This lowest temperature at which the gas ceases to exist is known as absolute zero. A British scientist, Lord Kelvin, suggested a new scale of temperature based upon the sources of zero. This is called absolute scale of temperature or Kelvin temperature scale, indicated by writing the letter K. Thus, minus 273 degrees Celsius equal to 0 Kelvin. This relationship between Kelvin scale and Celsius scale is Kelvin temperature equals to Celsius temperature plus 273. T in Kelvin equal to T in degree Celsius plus 273, where T is temperature on Kelvin scale and T is temperature on Celsius scale. Celsius scale is converted into Kelvin scale by addition of 273. Alternate statement of Charles' law. Equation 1 can be written as Vt equal to V0 T plus 273 upon 273. Putting 273 plus mol T equals to capital T in equation 2, we get Vt equal to V0 T capital T upon 273. Putting 273 equal to T naught, we get Vt equal to V naught capital T upon capital T naught, or Vt upon V naught equal to capital T upon capital T naught, or Vt upon capital T equal to V naught upon T naught, or V is proportional to temperature at constant pressure. Thus, Charles' law may be also stated as that at constant pressure, the volume of given mass of gas is directly proportional to the absolute temperature. Let V1 be the volume of certain mass of gas at temperature T1 and pressure P. If the temperature is changed to T2, keeping pressure constant, the volume changes to V2. Then according to Charles' law, V1 upon T1 equal to V2 upon T2 at constant pressure. Number 3. Avogadro's law. V proportional N at constant temperature and pressure. This law relates the volume of a gas to the number of molecules at constant temperature and pressure. It was put forward by Amedeo Avogadro in 1811. Avogadro's law states equal volume of all gases under similar conditions of temperature and pressure contain equal number of molecules irrespective of the nature of gas. It is known that 1 mole of any gas contains 6.023 into 10 to the power 23 molecules. Also that 1 mole of all gases at 273 Kelvin and 1 atmospheric pressure occupy a volume of 22.4 liters. This means that as long as the temperature and pressure remains constant, the volume of the gas is directly proportional to the number of molecules. Mathematically, Avogadro's law may be expressed as V proportional to capital N, where T and P are constant. Further, as the number of molecules of gas is directly proportional to its number of moles, small n, thus V is proportional to N, where similarly T, temperature and P, pressure are constant. Now we move forward to Graham's law of diffusion. Graham's law of diffusion states that the rate of diffusion of a gas is inversely proportional to the square root of the density of the gas at constant pressure. Mathematically, R proportional 1 upon under root D, where D is density at constant pressure, where R is rate of diffusion and D is density. When two different gases are under consideration, then according to Graham's law, the rates of diffusion of different gases are inversely proportional to the square root of the densities under similar condition of temperature and pressure. Mathematically, R1 upon R2 equal to under root D2 upon D1. Further, as 2 multiply vapor density equal to molecular mass, then we can write R1 upon R2 equal to under root M2 upon M1. If two gases diffuse under different pressures, say P1 and P2, then the rate of diffusion varies directly with pressure. In other words, greater the pressure, greater is the rate of diffusion. Hence, Graham's law can also be written as R1 upon R2 equal to P1 upon P2 in under root D2 upon D1, or equals, which implies P1 upon P2 under root M2 upon M1. Now we move forward to Dalton's law of partial pressure. This law relates the pressure of the mixture of non-reacting gases containing in a vessel to their individual pressure. This law states that at constant temperature, the pressure exerted by a mixture of two or more non-reacting gases enclosed in a definite volume is equal to the sum of the individual pressure which each gas would exert if present alone in the same volume at the same temperature. This individual pressure of the gas is known as its partial pressure. Mathematically, Dalton's law can be written as P equal to P1 plus P2 plus P3 at constant temperature and volume, where P is total pressure of the mixture of non-reacting gases and P1, P2, P3 are the partial pressure of the gases. Now we move towards ideal gas equation. The combination of Boyle's law, Charles' law and Avogadro's law leads to the equation which relates the variable pressure, absolute temperature, volume and number of moles. This equation is so formulated it is called combined gas law or gas equation. According to Boyle's law, V is inversely proportional to pressure at constant temperature. According to Charles' law, V is directly proportional to T at constant pressure. According to Avogadro's law, V is directly proportional to N at constant temperature and pressure. Combining these three laws, we get V is directly proportional to NT and is inversely proportional to P, or PV directly proportional to NT, or PV equals to nRT. This is known as equation 4. This equation 4 is called ideal gas equation. In this equation, R is the constant of proportionality known as gas constant. It is independent of amount and nature of the gas. Now we move towards nature of gas constant R. Ideal gas equation is PV equal to nRT, or R equal to PV upon NT, which is pressure into volume divided by moles into temperature in Kelvin. Since pressure is defined as force per unit area, R can be further simplified as pressure. In place of pressure, we can write force upon area into volume, moles into temperature in Kelvin, which is in the denominator, which equals force into length upon moles into temperature. Since force into length is work, so ultimately R becomes work upon moles into temperature in Kelvin. This R represents work done per degree per mole. These dimensions of gas constant R are energy per mole per Kelvin. Since work is expressed in different units in different systems, thus R has different numerical values. Numerical values of gas constant R. Since R equal to PV upon NT, therefore the numerical value of R depends upon units in which pressure and volume are expressed. The value of R is calculated for 1 mole of gas at NTP or STP conditions when pressure and volume are expressed in different units. When pressure is expressed in atmosphere and volume in liter for 1 mole of gas at NTP, the value of R is obtained in liter atmosphere per degree per mole. P equals to 1 atmosphere, V equals to 22.4 liter, T equal to 273 Kelvin, N equals to 1 mole. So R equal to PV upon NT, 1 atm into 22.4 liters divided by 1 mole into 273 Kelvin. So the value of R is 0.0821 liter atm Kelvin inverse mole inverse. When pressure is expressed in bar and volume in decimeter cube, 1 mole of any gas at 1 bar pressure and 273 Kelvin occupies a volume of 22.7 decimeter cube or 22.7 liter. So in this case the value of R becomes 0.0831 bar decimeter cube Kelvin inverse mole inverse. In SI unit, pressure is expressed in Pascal and volume in meter cube. So the value becomes 8.314 Pascal meter cube Kelvin inverse mole inverse. In Celsius unit, when pressure is expressed in mole inverse dynes per square centimeter, then the value of R becomes 8.314 into 10 to the power 7 ergs Kelvin inverse mole inverse. Further, we know 4.183 into 10 to the power 7 ergs equal to 1 calorie. So the value of R becomes 2 calorie Kelvin inverse mole inverse. Now we move towards the kinetic theory of gas. Kinetic theory of gas was the first theoretical attempt to explain the behavior of gases. The various gas laws were based on the experimental fact. There was no theoretical background to justify them. So in order to account for the observed properties of gases, a model was proposed which takes into consideration the molecular nature as well as the kinetic nature of gases. In 19th century, Maxwell, Boltzmann and Clausius put forward a theoretical model known as kinetic molecular theory of gases, which provided theoretical basis for various gas laws. The main postulates of this theory are given below. Postulates of kinetic theory of gases. The main postulates of the theory are: all gases are made up of large number of extremely small particles called molecules. The molecules of a given gas are identical in size, shape and mass. The molecules of the gas are separated from one another by such large spaces so that the actual volume occupied by the molecules is negligible as compared to the total volume of the gas. There are no attractive forces between the molecules of the gas. They move completely independently. The molecules are in a state of ceaseless and random motion in all directions. During their motion, they collide with one another and also with the walls of the container. The collisions of the molecules with one another and with the walls of the container are perfectly elastic, so that no energy is lost during collisions. However, the energy may be redistributed between molecules during collisions. The pressure of the gas is due to collisions of the gas molecules against the walls of the container. Due to collisions, the molecules possess different velocities and hence different kinetic energies. However, the average kinetic energy of the molecules is directly proportional to the absolute temperature. The motion of the molecules is unaffected by the force of gravitation. Now we move towards kinetic gas equation. Kinetic gas equation is a mathematical expression derived from the postulates of kinetic theory of gases. This equation relates pressure and volume of n molecules of a gas at a given temperature to the root mean square velocity. Kinetic gas equation is derived as follows. Consider a certain amount of gas enclosed in a cubical box at a particular temperature. Suppose that each length of the box is 1 L centimeter, number of gas molecules n, mass of each molecule of gas m. According to kinetic theory of gas, the molecules are moving randomly in all directions with different velocities. Consider a molecule moving with velocity v centimeter per second in any direction. Velocity is a vector quantity and can be resolved into three mutual perpendicular components: Vx, Vy and Vz along x, y and z axis respectively. The component velocities are related by the expression v square equal to vx square plus vy square plus vz square. Consider a molecule moving along x-axis due to velocity vx. The molecule will strike the opposite faces A and B. Momentum of the molecule before striking face A equals to mvx. As the collision with phase A is elastic, the molecule returns back with the same velocity but in opposite direction. Due to change in direction, the velocity is taken as negative. Vx. The momentum of molecule after striking phase m equal to m multiply minus Vx equal to minus mvx. The net change in momentum of the molecule is single collision with phase A, mvx minus of minus mvx, which gives 2 mvx. Therefore, a molecule imparts a momentum of 2 mvx to the phase A in one collision. Collision calculation of number of collision per second on phase A due to Vx component. For next collision on phase A, the molecule has to travel from phase A to B and then back from B to A. That is, it has to travel a distance of L plus L 2L centimeter. Since the velocity of the molecule is Vx centimeter per second, therefore distance traveled by molecule in 1 second is Vx centimeter. Since the molecule collides once on phase A after traveling a distance 2L centimeter, therefore the total number of collisions on phase A in 1 second equal to Vx upon 2L. Change of momentum of molecule due to collision with phase A in 1 second equal to momentum transferred in one collision multiplied by number of collisions per second, which gives 2 mvx multiply vx upon 2l equals to mv square x upon l. Similarly, change of momentum of molecule due to collision with phase B in 1 second, mv square x upon l. Total change of molecule due to collision with phases A and B per second equals to 2 mvx square upon l. Similarly, change of momentum per second on two phases along y-axis and along z-axis are 2 mv square y upon l and 2 mv square z upon l respectively. Therefore, total change of momentum of one molecule per second on all six phases equal to mv square x upon l plus 2 mv square x upon l plus 2 mv square y upon l plus 2 mv square z upon l, which implies 2m upon l in bracket v square x plus v square y plus v square z. Since v square equal to v square x plus v square y plus v square z, so it ultimately becomes 2 mv square upon l. Similarly, the change of momentum on all six phases in 1 second for n molecules having velocities v, v1, v2, v3 and vn will be given by 2m upon l in bracket v square plus v1 square plus v2 square plus v square n, which will give us 2m multiply n upon l v square plus v1 square plus v2 square plus v square by n divided by n, which will ultimately become 2mn u square upon l, where u is root mean square velocity and is expressed as u equals to under root v plus v1 square plus v2 square plus v square n divided by n. Therefore, the change of momentum per second is the rate of momentum. But according to Newton's second law, the rate of momentum is called force. Thus, force exerted by n molecules on all six phases F equal to 2 mn u square upon L. By definition, pressure is force per unit area, so pressure becomes force upon area, which becomes 2 mn u square by L into 1 upon 6L square, which ultimately gives us 1 upon 3 mn u square upon V, where L cube equal to V, the volume of the cube, or PV equal to 1 upon 3 mn u square. This expression is called kinetic gas equation. Calculation of average translational kinetic energy of gas molecules. Using kinetic gas equation, the average translational kinetic energy of a molecule at temperature T of the gas can be calculated. The average translational kinetic energy of a molecule is 1 upon 2 mvu square at temperature T. The total energy of whole of the gas contains n molecule is Ke upon half mn u square. The kinetic gas equation is PV equal to 1 upon 3 mn u square, or which we will further simplify by multiplying it upon 2 by 3. So 2 by 3 into 1 by 2 mn u square equal to 2 by 3, where 1 upon 2 mn u square is kinetic energy. So PV equal to 2 by 3 kinetic energy. Comparing this equation with general gas equation PV equal to RT, we get RT equals to 2 upon 3 kinetic energy, or kinetic energy equal to 3 upon 2 RT for 1 mole of gas. The average kinetic energy per molecule can be obtained by dividing both sides of above relation by Avogadro's number n naught. Average kinetic energy for one molecule 3 by 2 RT upon n naught, or 3 by 2 upon KT, where K equals to R upon n naught and is called Boltzmann constant. Thus, kinetic energy is directly proportional to temperature T. From this expression, it is clear that translational kinetic energy of an ideal gas is independent of the pressure, the molecular mass, of the nature of the gas. It depends only upon absolute temperature T. Thus, at the same temperature, the average kinetic energy of hydrogen will be same as that of nitrogen. kinetic energy and concept of absolute temperature. The kinetic energy for 1 mole of ideal gas is kinetic energy equals 1 upon 2 m capital N u square, or kinetic energy directly proportional to u square. Further, from kinetic gas equation, we have derived that kinetic energy equal to 3 upon 2 RT, or kinetic energy is directly proportional to T. Thus, kinetic energy of an ideal gas is directly proportional to absolute temperature T. From expression 4 and 6, we get U square directly proportional to T, or U is directly proportional to under root T. Thus, mean square velocity of a gas is proportional to the square root of its absolute temperature. Now we will move towards deduction of gas laws from kinetic gas equation. Boyle's law. The law states at constant temperature the volume of given amount of gas is inversely proportional to its pressure. Mathematically it is expressed as V proportional to 1 upon P, or P equal to constant. Derivation of Boyle's law. Kinetic gas equation is P equal to 1 upon 3 mu square, which can be further simplified as 2 upon 3 into 1 upon 2 mu square, where m cross n equals to capital M, total mass of the gas. Kinetic energy of the gas is 1 upon 2 mu square. So the equation P equal to 2 by 3 into 1 by 2 mu square can be written as 2 by 3 into kinetic energy. According to kinetic theory of gases, the average kinetic energy of molecule is directly proportional to absolute temperature, that is kinetic energy proportional to T, or kinetic energy equal to K upon T, where K is constant of proportionality. So the equation P equal to 2 by 3 kinetic energy can be written as P equal to 2 by 3 KT. Right hand side of above equation is a constant quantity at constant temperature, hence P equal to constant at constant temperature. This is Boyle's law. Now we move towards Charles' law. This law states that at constant pressure, the volume of a given mass of gas is directly proportional to its absolute temperature. Mathematically, V is directly proportional to T, or V by T equal to constant. As already derived in equation 4, we have P equal to 2 by 3 Kt, or V by T equal to 2 by 3 Kp. The term 2 by 3 and Kp is constant at constant temperature. Hence, V by T equal to constant. This is Charles' law. Now we move towards Avogadro's law. This law states that equal volume of all gases under similar condition of temperature and pressure contain equal number of molecules. Derivation of law. The kinetic gas equation for any two gases can be written as P1 V1 equal to 1 upon 3 M1 N1 U square, or P2 V2 equal to 1 upon 3 M2 N2 U2 square. This equation can be expressed as P1 V1 equal to 2 by 3 into 1 by 2 M1 N1 U square, P2 V2 equal to 2 by 3 into 1 by 2 M2 N2 U2 square. If both the gases are at same temperature pressure, then P1 equal to P2 for equal volume of both gases, then V1 equal to V2. Combining these two conditions, we can write P1 V1 equal to P2 V2. This means left hand side of equations are equal. So 1 upon 3 M1 N1 U1 square equal to 1 upon 3 M2 N2 U2 square. Cancelling M1 by 3 and 1 by 3 on both sides, we get M1 N1 U1 square equals to M2 N2 U2 square. From kinetic theory of gas, we know that average kinetic energy of gas is directly proportional to absolute temperature. Since both the gases are at same temperature, then average kinetic energy of first gas equals to average kinetic energy of second gas. That is 1 upon 2 M1 U1 square equals to 1 upon 2 M2 U2 square. Cancelling 1 upon 2 on both sides, we get M1 U1 square equal to M2 U2 square. Putting this thing on M1 N1 U square and M2 N2 U square, we get U1 square equal to U2 square. We get N1 equals to N2. Hence, Avogadro's law is proved. Now we move towards ideal gas equation. For 1 mole of ideal gas, the gas equation is PV equal to RT. Kinetic gas equation is PV equal to 1 upon 3 MN square, or 2 by 3 into 1 by 2 MN square, or P by V equal to 2 by 3 kinetic energy. Since 1 by 2 MN square equal to kinetic energy. According to kinetic theory of gas, kinetic energy of molecule is proportional to its absolute temperature, that is kinetic energy is directly proportional to T, or kinetic energy equal to K upon T. This equation can be written as P equal to 2 upon 3 KT. The constant 2 by 3 K is equal to R, the gas constant, therefore equation becomes P equal to RT, which is the ideal gas equation for 1 mole of ideal gas. Now we move towards Graham law of diffusion. This law states that under similar condition of temperature and pressure, the rate of diffusion of gases are inversely proportional to the square root of the densities. Mathematically, it is R1 upon R2 equal to under root D2 upon D1, or R proportional to 1 upon D, where R is rate of constant diffusion and D is density. Kinetic gas equation is P equal to 1 upon 3 Mn U square, or 1 upon 3 Mu square, since m cross small n equals to capital M, total mass of the gas. or u square equal to 3 pv upon m, or 3 which implies 3p upon m by v, 3p by d, since m upon v is density, or u equal to under root 3p upon d. Thus rate of diffusion of gas is proportional to velocity u of the gas, that is more the velocity of molecules greater is the rate of diffusion. From equation 14 and 15, which are u equal to under root 3p upon d and u is proportional to r, which is equation 15, we can write r is proportional to under root 3p upon d at constant pressure. Above equation reduces to r proportional to under root 1 upon 1 by d, which is Graham's law. Now we move towards Dalton's law of partial pressure. This law states that at constant temperature, the pressure exerted by a mixture of two or more non-reacting gases enclosed in a definite volume is equal to the sum of individual pressure which each gas would exert if present alone in the same volume. Mathematically, P equals to P1 plus P2 plus P3, where P is total pressure of the mixture of gases at constant temperature and volume, and P1, P2 are the partial pressure of the gases. According to kinetic gas equation, P equal to 1 upon 3 mnu square, or P equal to 1 by 3 mnu square upon V. When first gas enclosed in a vessel of volume V, the pressure exerted by the gas is given by P1 equal to 1 upon 3 m1 n1 u1 square upon V. When second gas is put separately in the same container of volume V, the pressure exerted by the gas is P equal to 1 upon 3 m2 n2 u square u2 square upon V. Now these gases are put together in a container having volume V, then total pressure is given by P equal to 1 upon 3 m1 n1 u1 square by V plus 1 by 3 m2 n2 u square by V, or P equal to P1 plus P2. Hence Dalton's law from kinetic is derived from kinetic gas equation. Now we have some question. The students are requested to do the questions by themselves. Now we move towards Maxwell's distribution of molecular speed. According to kinetic theory of gases, the gas molecules are moving rapidly at random direction in all randomly in all directions. Hence, they undergo collisions with each other and with the walls of the container. Due to frequent collisions, the speed and direction of molecules keep on changing. So all the molecules in a given sample of gas do not possess the same speed. Even at a particular temperature, the speed of different molecules keep on changing. Most of the molecules have speeds close to average, and relative few molecules have speed far above or far below the average value. The manner in which the molecules of a gas have speeds the manner in which the molecules of a gas are distributed over the possible range of speed from nearly zero to very high values was worked out by Maxwell. Maxwell in 1886 pointed out that the distribution of speeds remain constant at a particular temperature, although the individual speeds of molecules may change, which implies that the fraction of the molecules with a particular speed remains constant. This distribution is known as Maxwell-Boltzmann distribution. Using the theory of probability, Maxwell showed that the actual distribution of molecular speed depends upon the temperature and molecular mass of gas. According to Maxwell distribution, the fraction of molecules having velocities between c and c plus dc is given by d and c by n equal to 4 pi in second bracket m upon 2 pi rt raised to the power 3 by 2, and in e raised to the power minus capital MC square divided by 2 RT c square dot dc, where dn is the number of molecules having velocity between c and c plus dc out of the total n molecules of gas, m is molecular mass of gas, and t is absolute temperature. This equation may be rearranged as 1 upon 1 by n dot d and c upon dc equal to 4 pi in second bracket m upon 2 pi rt raised to the power 3 by 2 e raised to the power minus mc square upon 2 divided by 2 rt c square. The term 1 upon n d n upon dc on the left side of equation gives the fraction of molecules in the speed range c and c plus dc per unit interval of the speed, and is thus the probability p of finding molecules having speed c. The plot of probability p against the speed of the molecule at a particular temperature is shown in figure 3. The curve so obtained is called Maxwell's distribution curve. The number of molecules within the range of c plus dc is determined by the product of ordinate 1 upon n dnc upon dc and the speed range dc, and is equal to dnc upon n, which is the fraction of molecules in the velocity range c plus dc. Hence, the area under the whole curve gives the total number of molecules, and the height of the ordinate at any value of c gives the fraction of molecules having that velocity. The important features of Maxwell distribution curves are as follow. The fraction of molecules with very low or very high speed is very small. The fraction of molecules possessing higher speed keeps on increasing till it reaches a peak, and thereafter it starts decreasing. The Maxwell fraction of molecules possess a velocity corresponding to the peak in the curve. The speed corresponding to the peak in the curve is referred to as the most probable velocity. The most probable velocity or speed of a gas is the speed possessed by the maximum fraction of gas molecules at a given temperature. It is denoted by alpha. Now, Van der Waals equation of state for real gas. The general gas equation P equal to nRT is applicable to ideal gases only. In order to get an equation applicable to real gases, the ideal gas equation was modified by Van der Waals by introduction of two correction atoms, one for the finite volume and the other for intermolecular forces of attraction and repulsion between the gas molecules. Now, point number one, correction due to volume correction. The volume occupied by the molecules is not negligible in comparison to the total volume. This means that molecules are not free to move in the entire volume V. Thus, the free volume available to the gas molecule is less than the observed volume. As a result, the ideal volume of gas is smaller than the observed volume V. Hence, some correction in terms has to be subtracted from the observed volume to get the ideal volume. Let V be the actual volume occupied by 1 mole of the gas molecule. As the gas molecules are in constant motion, it has been found that the effective volume occupied by the gas molecules is 4 times the actual volume of the gas molecule. Effective volume equal to 4 times V. The effective volume is represented by V, B, then the volume correction term for 1 mole of gas B equal to B. If V is volume occupied by 1 mole of gas, then the volume available to the molecule for free movement is V corrected equal to V minus B. For n molecules of gas, the correction term is Nb, so the corrected volume is given by V minus Nb. The constant B is called excluded volume or co-volume per mole of the gas. Its value depends upon the nature of the gas. It may be kept in mind that B is not equal to the actual volume of the molecules, but is a measure of effective size of the gas molecules. The value of B has been calculated to be 4 times the actual volume of the molecules. It can be calculated by considering a bimolecular collision between two rigid spheres. Gas molecules with radius equal to r, the distance of closest approach of molecules is 2r equal to sigma, the collision diameter. Therefore, two molecules cannot approach each other more closely than diameter sigma. In other words, the volume occupied by a sphere of radius 2r represents the excluded volume for two molecules. Now, thus, the excluded volume per pair of gas molecules equal to 4 by 3 pi 2r cube, which equals to 8 by 4 by 3 pi r cube. The excluded volume per molecule 1 by 2 into 8 4 by 3 pi r cube, or 4 into 4 by 3 pi r cube, which gives 4m, where Vm equal to 4 by 3 pi r cube is the actual volume of single molecule. Thus, excluded volume for 1 mole of gas B equal to 4 Vm cross n, or B equal to 4 Vmn for 1 mole of gas, where n is Avogadro's number. The constant B is called Van der Waals constant. Correction due to intermolecular forces, pressure correction. Pressure of the gas is due to forces with which the gas molecule collide with the walls of the container. As there are some intermolecular forces of attraction exist between the molecules of real gases at low temperature and high pressure, therefore the molecules striking the walls experience an upward pull due to surrounding gas molecules. Consider a molecule in the middle of the container as shown. The molecule experiences a uniform attraction by the neighboring molecules. The attractive forces cancel out each other, and there is no net pull exerted on such a molecule. On the other hand, when the molecule is going to strike the wall, it experiences a backward drag due to inward pull of the neighboring force. Because of the inward pull, therefore the observed pressure P is less than the ideal pressure Pi. Thus, in order to calculate ideal pressure, some correction terms should be added to the observed pressure. Ideal pressure Pi equal to P plus P, where P is P plus small p, where small p is correction term due to inward pull. The inward pull small p on the molecule is directly proportional to number of molecules per unit volume in the bulk of the gas, or second number point, the number of molecules striking the wall per unit area at any given time. Both these factors are proportional to the square of the number of molecules per unit volume, n by V, or the square of the density of the gas. Hence, pressure correction P is directly proportional to N by V square, or P equal to A upon N square upon V square, where A is constant which depends upon the nature of the gas and is called van der Waals constant. Thus, ideal pressure becomes Pi equal to P plus A upon V square for 1 mole of gas, or Pi equal to P plus A N square by V square for N mole of gas. Substituting the value of ideal gas volume and ideal pressure in ideal gas equation, we get P plus A N square by V square multiply V minus N equal to nRT. This is van der Waals equation of state for N moles of gas. For 1 mole of gas, it becomes P plus A upon V square V minus P equal to RT. The constant A and B are called van der Waals constant. Significance of van der Waals constant. The value of van der Waals constants A and B depends upon the nature of the gas. Significance of A. The value of van der Waals constant A gives an idea of the magnitude of attractive forces between the molecules of gas. Larger the value of A, larger is the intermolecular attraction between among the gas molecules. In other words, larger the value of A, greater is the strength of van der Waals interaction. Now, the value of A for hydrogen and helium are very small, indicating that forces of attraction in these gases are very weak. The lower value of A reflects lesser tendency of these gases to be liquefied. As the value of A increases, the intermolecular forces of attraction increases. Consequently, the ease of liquefaction of gas increases. Thus, ammonia is more easily liquefiable as compared to methane, N2O2, H2 and He. Significance of constant B. The constant B is called co-volume or excluded volume per mole of the gas. It relates to incompressible volume of the molecules and measures the effective size of gas molecules. The value of B remains constant over a large range of temperature and pressure. This indicates that gas molecules are incompressible in nature. Units of van der Waals constant or units of A. The constant A is related to correction pressure as P equal to A n square by V square, A equal to P into V square by N square, pressure into volume square by mole square. In CGS, it is P is taken in atmosphere and V is taken in liters. So for A, atm into liter square by mole square, or atm liter square mole inverse square. If volume is expressed in dm decimeter cube, then CGS unit are atm decimeter cube decimeter whole to power 6 mole inverse square. CGS unit of B. B is simply volume, hence its unit are same as volume units of volume. CGS unit is liter mole inverse. SI unit of A is Newton meter square mole inverse square, or Pascal meter raised to power 6 mole raised to power minus 6. If volume is expressed in decimeter cube and pressure in Kelvin Pascal, then unit of A are Kelvin Pascal decimeter cube raised to power 6 mole inverse mole raised to power minus 2. SI units of B. If volume is in meter, then B equal to m cube mole inverse. If volume is in decimeter cube, then B is decimeter cube mole inverse. The unit of A and B in CGS and SI have been summarized. Expression of behavior of real gas on the basis of van der Waals equation. For 1 mole of real gas, van der Waals equation is P plus A upon V square multiply V minus B equal to RT at low pressure. When pressure P is low, the volume V of the gas is very large. Hence, the both terms A and B can be easily neglected in comparison to V. Therefore, equation reduces to PV equal to RT. The real gas obeys ideal gas equation and shows nearly ideal behavior at extremely low pressure. At moderate pressure, when the pressure is moderate, the volume decreases. Hence, the term A upon V square becomes appreciable. Hence, the term A upon V square is in equation cannot be neglected. At moderately low pressure, the volume V is sufficiently large, so the term B can be neglected in comparison to V. So van der Waals equation becomes P plus A upon V square by V equal to RT. PV plus A by V equal to RT. PV equal to RT minus AB. A upon V, or PV by RT equal to 1 minus A upon VRT. Z equals to A minus A upon VRT, or Z is smaller than 1. Under the condition of moderate pressure, PV is less than RT by factor A by V, or we can say that compressibility factor is less than 1. At high pressure, when the pressure is very high, the volume V becomes extremely small, so that term V cannot be ignored. But at high pressure, the term A by V can be neglected in comparison to P. This van der Waals equation reduces to PV equal to RT plus PV, or PV by RT equal to 1 plus PB by RT, or Z equal to 1 plus PB by RT, or the compressibility factor Z is greater than 1. So as the pressure increases, and the value of Z becomes greater than unity. Further, the value of Z increases as the pressure is increased. This explains the upward trends of the plot of Z versus P. at high temperature. At a given pressure, if the temperature is sufficiently high, the volume V becomes considerably large, so that factor E by V square is negligible in comparison to P. Also, B can be neglected in comparison to large value of V. The van der Waals equation reduces to ideal gas equation, P V equal to RT. This explained why real gases behave nearly ideally at high temperature, at very low pressure and very high temperature. Under these conditions, volume V becomes so large that both the terms A upon V square and B can be neglected. The van der Waals equation reduces to PV equal to RT. Hence, under these conditions, the real gases approach ideal behavior. Exceptional behavior of hydrogen and helium. The behavior of hydrogen and helium is exceptional because for these gases the compressibility factor always increases with increase in pressure. This is because both the hydrogen and helium have very small masses. As a result, the attractive forces between their molecules are negligible. Hence, the term A for hydrogen and helium is extremely small. Therefore, the term A upon V square is negligible at all pressure and at ordinary temperature. Thus, van der Waals equation reduces to PV equal to RT plus PB, or PV upon RT plus 1 upon PB by RT, or Z equal to 1 plus PB by RT. As Z is always greater than unity, so the Z versus P curves for H2 and HE always lies above the ideal gas curve and show upward trends with increase in pressure. Hence, H2 and HE always show positive deviation which increases with increase in pressure. Limitations of van der Waals equation. The van der Waals equation is a significant improvement over the ideal gas equation as it explains accurately the behavior of real gases over a wide range of temperature. However, this equation cannot be generalized because the van der Waals constant are empirical constant. Their values depend upon the nature of the gas. For example, the value of B for large molecule is larger, therefore the value of effective volume for large molecule is large. Also, since large molecules have larger surface area, the intermolecular attraction and therefore the value of A for such molecule is also large. Secondly, the van der Waals equation shows appreciable deviation when pressure is too high or the temperature is too low. This is because the values of A and B vary with temperature and pressure. When the pressure is increased, the value of B decreases. Similarly, if B is kept constant, on decreasing temperature, the value of A increases because the molecules come closer, resulting in increasing or of intermolecular attraction. Intermolecular attractive forces. Thus, van der Waals equation is of limited accuracy and starts showing more and more deviation at high pressure and low temperature. Now we move towards other equation of states. Van der Waals equation is an improvement over ideal gas equation, but it does not explain the exact behavior of real gases. A number of other equations of state have been proposed from time to time to explain the PVT relations of gases. A brief description of some important equations of state is given below. Clausius equation. R. Clausius in 1880 considered that the intermolecular attraction term A varies inversely with temperature. Clausius replaced the term A by V square in van der Waals equation by the term A upon T in bracket V plus C whole square, where C is another constant. According to Clausius equation, P plus A upon N square T V plus C square V minus N equal to RT, where A, B and C are called Clausius constant. Now, Berthelot's equation. Berthelot gave another form of equation by eliminating the constant C from Clausius equation. The equation due to Berthelot is P plus AN square TV square V minus NB by nRT, where A and B are called Berthelot's constant and depend upon the nature of the gas. Dietrich equation. Dietrich in the year 1889 proposed that the gas molecules in the bulk have lower potential energy than those at the walls of the container. This is because of the intermolecular attraction felt by the molecules in the bulk and those at the walls. Dietrich proposed an exponential factor to account for the effect of intermolecular attraction on the pressure exerted by the gas. Dietrich suggested the following equation of state. P upon V minus N be equal to nRTE E whole raised to power minus En upon RTV for 1 mole of gas. The equation becomes P multiply V minus B RT E raised to power minus A upon RTV, or P equal to RT V minus B E whole raised to power minus A RTV. At low pressure, the volume of the gas is large, therefore B may be neglected in comparison to V. Factor A upon VRT will also be small, hence E whole raised to power minus A upon VRT equal to 1 minus A upon RTV, or P equal to RT by V minus A upon V square. This equation is same as van der Waals equation, hence at low pressure, Dietrich equation is identical with van der Waals equation. At high pressure, the equation gives better result than van der Waals equation. Campbell-Onnes equation, virial equation. Campbell-Onnes equation is the most general equation of state for the gases. It is an empirical equation written in the written in the following form, in which PV for real gases is expressed as a power series in P. PV equal to A plus BP plus Cp square plus dP cube. P is the pressure in atmospheres and V is molar volume of gas in liter. A, B, C and D are called first, second, third and fourth virial coefficients respectively. It may be noted that the virial coefficients depend on the nature of the gas, hence the value is different for different gases. The coefficient A, B, C and D are pressure dependent. At low pressure, only the first virial coefficient A is significant and is equal to RT. However, at high pressure, the contribution due to other virial coefficients also become important. Kamerlingh-Onnes equation is also written by expressing the compressibility factor Z for real gases as a power series in 1 by V. Z equal to PV plus RT equal to 1 plus B by V plus C by V square plus D by V cube plus so on. Where B, C and D are called second, third and fourth virial coefficients respectively. These coefficients are temperature dependent but do not depend upon pressure. In general, the numerical value of virial coefficients decrease sharply with the higher power of the volume. Reduction of van der Waals equation to virial equation. The van der Waals equation of state for real gas is P plus A upon V square V minus B RT, or P equal to RT V minus B minus A upon V square. Multiplying both sides by V upon RT, we get PV by RT equal to V upon V minus P minus A upon V by RT. On rearranging this equation, we get Z equal to 1 minus B by V whole raised to power minus 1 minus A upon VRT. At low pressure, volume is large, therefore factor V by V is very smaller than 1. Thus the term 1 minus B by V whole raised to power minus 1 can be expanded as 1 minus x whole raised to power minus 1, 1 plus x square plus x cube. Similarly, 1 minus B upon V whole raised to power minus 1 equal to 1 plus B by V plus B by V square plus B by V cube. Substituting these values in equation, we get Z equal to 1 plus B by V plus B by V square plus so on minus A upon VRT. Rearranging this equation, rearranging the above equation, we can add Z equal to 1 B by V minus A by VRT plus B by V square plus so on. And this is so the final expression for virial equation is P equal to RT in bracket 1 plus B by V plus C by V square plus so on, which is known as virial equation. So here are some worked examples. The students are suggested to these examples by themselves. Now application of van der Waals equation. Calculation of boil temperature. The Z versus P curve of the same gas at different temperature shows that at low temperature the curve shows minimum. As the temperature is raised, the minimum in the curve shifts upward. At an intermediate temperature called the boil temperature, the value of Z remains close to unity over a large range of pressure. In other words, at boil temperature, a real gas obeys Boyle's law for range of pressure. Mathematically, the Boyle's temperature may be defined as the temperature at which limit P tends to 0 dF by PV upon dP equal to 0. The boil temperature TB can be easily obtained from van der Waals equation. The van der Waals equation for 1 mole of gas is P plus A upon V square V minus B equal to RT. It may be written in the form P equal to RT V minus B minus A upon V square, multiplying both sides by V. We get P equal to RT V minus VB minus A by V. Differentiating with respect to P at constant temperature, we obtain the following expression: T equal to A upon RB 1 minus B by V upon R square. When P tends to 0, the volume will be infinite. Thus the equation reduces to TB equal to A upon RP. Further, it can be shown that at Boyle's temperature, the van der Waals equation reduces to ideal gas equation. Effect of temperature on the distribution of speeds. It may be noted that fraction of molecules having a particular most probable speed remains same so long as the temperature of the gas remains same. However, on increasing the temperature of the gas, the molecular motion increases consequently. The value of most probable speed alpha also increases with increasing temperature. In fact, the entire distribution curve shifts towards right with rise in temperature. With increase in temperature, following changes are observed. The entire curve becomes flatter and shifts towards right. The value of most probable speed increases. The fraction of molecules having most probable speed decreases. The fraction of molecules having higher speed increases. The fraction of molecules having lower speed decrease with increase in temperature. However, the area under the two curves remains the same because the area under the curve represents the number of molecules in a gas sample. Now we move towards different types of molecular velocities. Molecular velocities are generally expressed in three different types: most probable velocity, average velocity, and root mean square velocity. Now, most probable velocity alpha. It is the velocity possessed by maximum fraction of total number of molecules of the gas at particular temperature. It is given by the expression alpha equals to under root 2 RT upon m, where m is molecular mass of the gas. Now we move towards average velocity V. It is the average of the different velocities of all molecules present in a given sample of gas at particular temperature. If V1, V2, V3 are velocities of n different molecules, then V equals to V1 plus V2 plus V3 plus Vn divided by n, where n is total number of gas molecules. Alternatively, if V1 is the velocity of n1 molecule, V2 is the velocity of n2 molecule, and so on, then V equal to n1 V1 plus n2 V2 plus n3 V3 plus n upon Vn by n1 plus n2 plus n3 up to Vnn. Average velocity is given by the expression V equal to under root 8RT upon pi m. Now we move towards root mean square velocity U. It is the square root of the arithmetic mean of square of different velocities of the molecules of a gas at a given temperature. If V1, V2, V3 are the velocities of n different molecules, then U equals to in root V1 square plus V2 square plus V3 square plus up to Vn square divided by n. Alternatively, if V1 is the velocity of n1 molecule, V2 is the velocity of n2 molecule, then U can be written as n in under root n1 V1 square n2 V2 square n2 V2 square divided by n1 plus n2 plus n3 upon nn. Root mean square velocity can be calculated from the following expression: U equal to under root 3RT by m, or under root 3PV upon m, or under root 3P upon rho. Derivation of molecular velocity from Maxwell distribution expression. Maxwell distribution expression can be used to derive expression for most probable velocity, average velocity, and root mean square velocity. Now, most probable velocity. The expression for most probable velocity is alpha equal to 2 under root 2 RT upon m. It is the velocity possessed by maximum fraction of molecule of the gas. The condition of maximum can be obtained by differentiating Maxwell's distribution equation with respect to c and putting the result equal to 0. Thus we get d upon dc in bracket dn by n equal to d upon dc in third bracket 4 pi m 2 pi rt raised to the power 3 by 2 e minus e raised to the power minus mc square divided by 2 rt dot c square, which is equals to 0, or 4 pi in first bracket m upon 2 pi rt bracket close raised to the power 3 by 2 into d upon dc in third bracket e raised to the power minus mc square divided by 2 rt dot c square, which is equals to 0. In equation 2, the factor this is the equation that we just discussed was equation 2. In equation 2, the factor 4 pi in bracket m upon 2 pi rt raised to the power 3 by 2 is constant and cannot be 0. So d upon dc in third bracket e raised to the power minus mc square upon rt dot c square equals to 0, which gives us the value as c dot e raised to the power minus mc square upon 2 upon rt in bracket minus mc cube upon 2 by rt, which is equals to 0. The first two conditions for c equals to 0 and c equals to infinity correspond to the minima as there are no molecules having speed equal to 0 or infinity. However, the third condition determines the condition of maximum in the distribution curve, and the value of velocity obtained is the maximum probable velocity. Thus 1 minus mc cube upon 2 by rt equals to 0, or c equal to under root 2 rt by m. This c corresponds to the most probable velocity alpha, hence alpha equal to under root 2 by rt by m. Now we move towards average velocity v. This expression for the expression for average velocity is v equal to under root 8 rt by pi m. Average velocity is the summation of different velocities possessed by the molecules divided by the number of molecules of the gas. Assuming the molecules can have velocities ranging from 0 to infinity, the average velocity can be obtained by integration between limits 0 to infinity and dividing it by the total number of molecules, that is v or c equal to 1 upon n in integration sign 0 to infinity c d n c, or equal to integration sign 0 to infinity c dot d n c by n. where dc the number of molecules having speed c. Substituting the value of d and c by n from Maxwell distribution equation, we get v equals to integration sign 0 to infinity c dot 4 pi in bracket m upon 2 pi rt 3 by 2 e raised to power minus mc square upon 2 rt dot c square, or which implies 4 pi in bracket m upon 2 pi rt raised to power 3 by 2 integration sign 0 to infinity c cube e raised to power minus mc square upon 2 rt dot dc. Let m upon 2 rt equal to a, where a is constant, then above integration can be written as 4 by pi m upon 2 pi rt 3 by 2 raised to power 3 by 2 integration sign 0 to infinity e raised to power minus mc square by 2 rt dot dc c cube dot dc. Such as integral on solving gives us v equal to under root 8 rt by pi m. Now we move towards root mean square velocity u. The expression for root mean square velocity is u equal to under root 3 pi rt by m. The root mean square velocity is given as u square equal to 1 upon n in integration sign 0 to infinity c square dn. Maxwell distribution equation is dn n into 4 pi in under root m by 2 upon rt raised to power 3 by 2 e raised to power minus mc square upon 2 rt dot c square dc. Substituting value of dn into equation this, we get u square equal to 1 upon n in integration sign 0 to pi c square into n dot 4 pi in third bracket m upon 2 pi rt raised to power 3 by 2 e minus mc square divided by 2 pi rt c square dc. This integration is solved as follow from and after solving we get the value as u equal to under root 3 pi rt by m. Now relation between these three types of velocity. This relationship between three types of velocity can be derived as follows. The expression for most probable velocity alpha, average velocity v, and root mean square velocity u rms are a alpha equal to under root 2 pi r 2 rt by m, v equal to under root 8 rt by pi m, u equal to under root 3 rt by m. Comparing equation 1 and 3, we get a by u equal to under root 2 by 3 or alpha equal to alpha by u equal to under root 2 by 3 or alpha equal to under root 2 by 3 u, alpha equal to 0.816 u. On comparing v and u, we get v equal to 0.921 u. Alternatively, this relationship between alpha, u and v can be obtained directly as under root 2 rt by m is to under root 3 rt by pi m is to under root 3 rt by m, which eventually gives us value as 1.414 to the ratio 1.595 to the ratio 1.732. It is obvious that for a gas at temperature u is greater than v and v is greater than alpha. These velocities are graphically shown in Maxwell distribution curve. Now we move towards molecular collision in a gas. Kinetic theory treats the molecules as elastic spheres. Thus, during collision, the molecules are assumed to be rigid, non-interacting spheres with diameter rho, diameter sigma. It is also assumed that all the molecules move with speed, that is, the average speed v. In this section, we will discuss some of the collisions property of the gas molecules. Now we move towards collisional diameter. When the gas molecules approach each other to collide, there is a distance of closest approach beyond which they cannot come closer. At this point, the mutual repulsion between them due to electronic and nuclear repulsive forces becomes so strong that they are rebounded. At this point of closest approach, the direction of movement of two molecules gets reversed. Thus, collision diameter is the closest distance of approach between the center of two molecules. They just touch each other during a collision. It is denoted by sigma. While consider molecule collision, we assume that molecules are rigid spheres with diameter sigma. The identical molecules having diameter sigma will just touch each other when the distance between their center is sigma. These molecules will collide only when the distance between the center is less than molecular diameter sigma. From figure, it is obvious that collision's cross section is an area of imaginary sphere radius sigma around the molecule into which the center of other molecules cannot penetrate. Collision number and collision frequency. According to kinetic theory, we assume that molecules of gas are in constant random motion and are continuously colliding with each other. The gas molecules are assumed to be rigid spheres of diameter sigma. The collision occur only when the distance between the center of the two molecules lies within the collision diameter sigma. The number of collisions made by one molecule with other molecule in 1 second is called collision number, whereas the number of molecular collisions occurring per second per unit volume of gas is called collision frequency. For gas containing N molecules per unit volume, the collision number Nc is given by the expression Nc equal to under root 2 pi v sigma square N, and collision frequency Z is given by the expression Z equal to 1 upon root 2 pi v sigma square N square, where V equal to average velocity of molecules, N equal to number of molecules per unit volume of gas, sigma molecular diameter. This expression are derived from kinetic theory gas as follows. If n is the number of molecules per unit volume, then total number of molecules within the cylinder is pi sigma square v divided by n. Hence the number of collision made by one molecule with other molecule in 1 second is given by pi sigma square v upon n. So far we have assumed that only one molecule is moving and positions of all other molecules are fixed. However, in actual practice, all the molecules are not stationary. We must consider the relative speed of the colliding molecules. All the molecules are moving with an average speed v, and all types of collisions ranging from glancing collisions to head-on collisions may occur. The relative speed depending on the angle at which the molecules may collide. The speed in glancing collisions is is 0, and that is head-on collision is 2v. In general, most of the molecules collide at 90 degree to each other. Then the average velocity of the colliding molecule is under root 2v. Now point number A, glancing collision relative velocity is 0, head-on collision relativity is 2v, collision at right angle velocity is under root 2v relative. During its motion, the molecules A collide in 1 second with all the molecules that have centers within the cylinder of length v and radius sigma. In 1 second, molecules A travel a distance of v centimeter and sweep a cylinder volume pi sigma square v. When pi sigma square is called the collision cross section of the molecule. Collision frequency Z is directly proportional to average velocity of gas molecule, square of molecular diameter, and square of number of molecules per unit volume. Thus, substituting under root 2v in place of v, the number of collisions suffered by a single molecule per second per unit volume is given by Nc equal to under root 2 pi v sigma square n. The number Nc is called the collision number. The total number of collisions made by all the n molecules per unit volume of the gas can be obtained by multiplying b n times the value of Nc, that is Nc cross n equal to in bracket under root 2 pi v sigma square n cross n, or under root 2 pi v sigma square n square. The number Z is the collision frequency. Thus, the collision frequency is the number of molecular collision occurring per second per unit volume of the gas. Now, we move towards effect of temperature and pressure on collision frequency. It is clear that collision frequency varies directly with temperature. Hence, as the temperature is increased, the collision frequency also increases. The same conclusion can also be derived from equation 7, where it is seen that collision frequency is directly proportional to average velocity. On increasing temperature, the average velocity of the molecules increase. Therefore, collision frequency also increase. When pressure is increased, the number of molecular collisions increase, and it is clear from equation 7 and 9. Increase in pressure leads to increase in collision frequency. It may be noted that under ordinary condition of temperature and pressure, the value of collision frequency is very high. In a given sample of gas at room temperature, gas molecules undergo 10 to the power 25 to 10 to the power 28 collisions per centimeter per second. Now we move towards mean free path. The gas molecules are constantly moving randomly and are colliding with each other. A molecule moves in a straight line before colliding with other molecule. The distance traveled by a molecule before collision with another molecule is referred to the free path, as a molecular motion is random. So the distance traveled by a molecule before colliding with other molecule is not always the same. Sometimes the molecule travels short distance before collision, while at other times it may travel long distance to collide. Therefore, we take the average distance traveled by a molecule before colliding with other molecule. The mean free path is the average distance traveled by a molecule between two successive collisions. It is denoted by L. if p centimeter per second is the average velocity of the molecule, then the average distance traveled by the molecule in 1 second is v centimeter. If nc is the number of collisions a molecule undergoes per second, there is collision number, then mathematically mean free path is expressed by L equal to v upon nc, or nc equal to under root 2 pi v sigma square n, already derived. Therefore L equal to v upon under root 2 pi v sigma square n, or L equal to 1 upon under root 2 pi sigma square n. This equation indicates that mean free path does not depend upon the speed of molecules. Mean free path varies inversely with the square of molecular diameter. That means larger the molecular size, more frequent will be the collision, and consequently shorter will be the mean free path. Mean free path depends inversely on the member of molecules per unit volume of the gas. Hence, as the pressure increases and also the number of molecules increase, the mean free path increases. Effect of temperature and pressure on mean free path. From the equation for mean free path, it is clear that mean free path is inversely proportional to number of molecules per unit volume of gas. The ideal gas equation for n molecules of gas is P equal to nRT, or n by V equal to P upon RT, where n by V is the number of moles per unit volume of the gas and is represented by small n, so that n equal to n dash, so that n dash equal to P upon RT. Above expression is multiplied by Avogadro's number n naught, we get the number of molecules per unit volume. N equals to P upon n naught upon RT. Putting this value of n in equation, we get L equal to 1 upon under root 2 pi sigma square dot RT upon P n naught, or L equal to KT by under root 2 pi sigma square P, where K equal to R upon R naught. It follows that L is directly proportional to T upon P, thus L is directly proportional to T and L is inversely proportional to P. Since according to Gay-Lussac's law, P is directly proportional to T at constant volume, therefore under the this equation become L is proportional to constant. Thus there will be no effect of changing temperature or pressure on mean free path. The volume of the gas is if the volume of the gas is kept constant. Now here are some examples. The students are advised to do the questions by themselves. Now we move towards viscosity of gases. Viscosity is the property of fluids. Viscosity is the resistance to the flow of the fluid. It is the internal friction which opposes the relative motion of adjacent layers of a fluid. It may be defined as the resistance which a layer of fluid offers to the flow of another layer to the liquid. To understand the concept of viscosity in gases under the flow of gas in horizontal plane, we suppose that the gas is flowing in the form of number of horizontal layers as shown. Each layer is assumed to be made up of number of molecules which flow over each other in the parallel layers. This type of flow is called laminar flow. Consider the horizontal layers moving with velocity v1, v2, v3, v4. Assume that the layer touching the horizontal surface has zero velocity. The molecules of this layer have low momentum as the gas molecules are in continuous motion, so there is an interchange of molecules between two layers. As a result, some momentum of second layer passes on to first layer. Thus the molecules of first layer exert a retarding influence on the molecules of the second layer, and so on. The net effect is decrease in the relative moment of one layer over the other layer. In other words, there is a retarding effect due to internal friction between the molecules of various horizontal layers. The internal friction which opposes and retards the relative motion of adjacent layer of gas is called viscosity in gases. Viscosity is responsible for decrease in the relative velocity of one layer over the other. To maintain a uniform velocity difference between adjacent layers, a force must be applied along the direction of motion of layers. The force F required to maintain a uniform velocity difference dV between two parallel layers is directly proportional to the area A of each of the layer and velocity gradient dV upon dx. In the vertical direction where dx is distance between two layers, therefore force is directly proportional to A into dV upon dx, or force equal to n a dV upon dx, okay, where n is constant of proportionality and is called coefficient of viscosity. If a equal to 1 centimeter square, dV equal to 1 centimeter per second, then F equal to n. Thus coefficient of viscosity is defined as force per unit area in dynes per square centimeter that must be applied to maintain a velocity difference of 1 centimeter per second between two parallel layers 1 centimeter apart. Unit of coefficient of viscosity. Coefficient of viscosity is given by n equal to F by A dx upon dv. Okay, in CG unit the force is expressed in dynes, so we get n equal to dynes second centimeter square. In CGS unit, the coefficient of viscosity is expressed in poise unit, where 1 poise equal to 1 dyne second centimeter square. Therefore, 1 poise equal to 1 gram centimeter cube second inverse. Sometimes the smaller units centipose, millipose, micropose are used. In SI system, the unit of viscosity are Newton meter square into second. Relationship between mean free path and coefficient of viscosity. Maxwell showed using simple kinetic theory that for the gaseous molecules considered as Hertz sphere, the coefficient of viscosity n is given by n equal to 1 upon 3 mn VL, where m is mass of the gas molecule, n number of molecules per unit volume, v average velocity, L equal to mean free path. This relation is derived as follows. Consider the flow of gas on horizontal plane. We assume the gas is flown in the form of horizontal layer parallel to each other, and each layer contains large number of gas molecules. The velocity of the layer touching the horizontal plane is 0. As we move upward, each layer has slightly higher velocity. There is uniform velocity gradient in the vertical direction between the successive layers. For convenience, consider 3 horizontal layers designated as P, Q and R. Let dV upon dx is the velocity gradient, where dV is the difference in velocity between adjacent layers and dx is the distance between them. Then the velocity of the layer at height h is given as dV upon dx cross h. Gas molecules are in continuous motion, so an interchange of molecules occur between two layers. If you observe a layer at height h, if L is the mean free path of gas molecules, then the molecules in the layer at height h collide and interchange with the layer at a distance L above it and a distance L below it. Velocity of gas molecules in the layer P equal to h minus L dV upon dx. Velocity of gas molecule in the layer Q, which equals to h plus L dV upon dx. Due to interchange of gas molecule between adjacent layers, there is transfer of momentum from one layer to another layer. Consider the layer P at height h. The molecules from upper layer R will bring extra momentum to this layer, while molecules from lower layer P will decrease the momentum of layer Q. We will calculate the rate of flow of momentum from layers P and Q to layer R. It is assumed that at any time 1 upon 1 by third of the gas molecule in a layer are moving along each other of the three perpendicular direction. Then 1 by sixth of the molecules are moving in upward and 1 upon sixth are moving in downward direction. If n is the number of molecules per unit volume and v is the average velocity, then the number of molecules passing downwards or upwards through an area of 1 centimeter square per second is 1 upon 6 nv. Let m is the mass of molecule from the layer P. The momentum transferred upward per square centimeter per second is 1 upon 6 mnv h minus L dV upon dx. The momentum transferred by the molecules moving downward from layer R to layer P per square centimeter per second. The net downward flow of momentum per second towards the layer P is 1 upon 3 mnvl dV upon dx. Since momentum transferred per second is numerically equal to force, therefore the force acting on 1 centimeter square area of the layer to maintain a uniform velocity difference F equal to 1 upon 3 mnvl dV upon dx. Comparing this with equation, we get n equal to 1 upon 3 mnvl. Expression 3 is Maxwell equation for coefficient of viscosity. It relates coefficient of viscosity and mean free path. In this equation, m cross n equal to L, the density of the gas, hence it can be written as n equal to 1 upon 3 rho v L. Calculation of mean free path. Using Maxwell equation, according to Maxwell equation, n equal to 1 upon 3 rho v L, or L equal to 3 upon n p v, or rho equal to m by v equal to p m by rt, or v equal to under root 8 rt upon pi m. Substituting these values in equation, we get L equal to 3 upon 2 p by pi rt 2m into n. Thus, knowing n, the mean free path can be calculated at a given temperature and pressure alternatively. Thus, mean free path can be calculated if n and density of the gas rho are known and particular temperature. Using Chapman's equation, according to this equation, L equal to 2 n upon rho v, putting rho equal to pm upon rt and v equal to under root 8 rt by pi m. In this equation, we get L equal to 1 upon under root 2 p into under root pi rt by m cross n. Now we move towards the topic: effect of pressure on coefficient of viscosity of gas. The mean free path and the coefficient of viscosity are related as n equal to 1 upon 3 mn vl, where m is mass of one molecule of gas, n equal number of molecules per unit volume, p is average velocity, L is mean free path. Average velocity v equal to 8 kt by pi m whole under root. The mean free path L equal to 1 upon under root 2 pi sigma square n, where sigma is molecular diameter. Putting the values of V and L in equation 1, we get n equal to 1 upon 3 mn under root 8 kt by pi m into 1 upon under root 2 pi sigma square n, or n equal to 2 by 3 under root mkt by pi cube pi raised to the power 3 by 2 sigma square. Now we move towards effect of temperature on coefficient of viscosity. Equation shows that n is proportional to n, that coefficient of viscosity is directly proportional to under root T. Therefore, the coefficient of viscosity of gases increase with increase in temperature. This is because at high temperature the kinetic energy of molecules increase, so the molecules must so the molecules move faster. As a result, there is more transfer of momentum, hence there is increase in viscosity. It is found that actually viscosity increases much more rapidly than shown by the relation coefficient of viscosity directly proportional to under root T. Sutherland gave the relationship between coefficient of viscosity and temperature as coefficient of viscosity and coefficient of viscosity dot under root T upon 1 plus C upon T, where N naught and C are constant of gas and are called Sutherland constant. Now we move towards calculation of molecular diameter from coefficient of viscosity. Coefficient of viscosity and mean free path are related by the expression n equal to 1 upon 3 mn VL. Further, L equal to 1 upon under root 2 pi sigma square n. Substituting for L in equation 1, we get n equal to 1 upon 3 m and v cross 1 upon under 2 pi sigma square n, or n equal to 1 upon 3 mv dot under 2 pi square. Thus, knowing m, v and the molecular diameter of gas can be calculated. Chapman gave a more precise treatment to equation 3 and modified n equal to 0.499 mv upon under 2 pi sigma square upon c by t, where c is Sutherland constant. These are some of the questions that the students are advised to do by their own. Now we move towards ideal and non-ideal or real gases. A gas which obeys the general gas equation P equal to nRT and other gas laws at all temperature and pressure is called an ideal gas or perfect gas. However, experiments show that gas laws are obeyed fairly well at low pressure and moderately high temperature. But as the pressure is increased or the temperature is decreased, the deviation from ideal behavior are observed. In fact, no gas obeys gas laws or ideal law equation over the entire range of temperature and pressure. We can say no gas is perfectly ideal. The gases which do not obey the gas laws and ideal gas equation at all temperature and pressure are called non-ideal or real gases. In other words, the real gas is the one which obeys gas law under the condition of low pressure and moderately high pressure. All gases are real gases and they show ideal behavior to different extents. Most of these show ideal behavior at low pressure and high temperature and may get induced, and other scientists have made extensive study of the behavior of various gases under different conditions of temperature and pressure. They concluded that real gases do not obey the ideal gas equation under all conditions of temperature and pressure. It is observed that easily liquefiable gases like ammonia, carbon dioxide, sulfur dioxide, etc. show larger deviation from ideal behavior than gases such as hydrogen, nitrogen, oxygen, etc. A comparison between non-ideal and ideal gases. Ideal gases obeys gas law and ideal gas equation at all temperature and pressure, whereas non-ideal gas obeys low gas only under pressure and low pressure and moderately high temperature. It obeys ideal gas equation P equal to nRT. It obeys van der Waals equation P plus A n square by V square upon V minus NB upon nRT. An ideal gas does not actually exist, it is hypothetical. All the gases which exist are real. Non-easily liquefiable gases like H2, N2, O2 show nearly ideal behavior. Easily liquefiable gases like NH3, etc. show larger deviation from behavior. There are negligible intermolecular forces of attraction in an ideal gas. The intermolecular force of attraction is appreciable, especially at low temperature and high pressure. Deviation from ideal behavior. An ideal gas obeys gas law or the ideal gas equation P equal to nRT under all condition of temperature and pressure. In fact, no gas is ideal. Almost all gases show deviation from ideal behavior. The real gas obeys gas law only under certain condition of temperature and pressure. The magnitude of deviation from the ideal behavior may not be seen from the deviations from Boyle's law. According to Boyle's law, PV equal to constant at constant temperature. Hence, for an ideal gas, the plot of PV versus P at constant temperature should have a straight line parallel to abscissa. However, we do not get a straight line. There is significant deviation from ideal behavior. Plots of PV versus P for real gases are shown In the figure, two types of curves are obtained. Gases like H2 and HE obey boil slow and very low at very low pressure, but PV increases continuously as the pressure increases. Gases like CO, CO2, and CH4 show decrease in PV in the beginning, passes through a minimum, which is different for different gases, and then increases continuously with pressure. Measurement of deviation in terms of compressibility. In case of real gases, the deviation from ideal behavior can be measured in terms of compressibility factor. It is defined as Z equal to PV upon nRT or PV upon PV ideal. In case of an ideal gas, Z or compressibility factor is 1 and it is independent of temperature and pressure. For real gases, Z is not equals to 1. It is either less than or greater than 1. The extent of deviation from Z equal to 1 is a measure of non-ideality of the gas. For real gases, the compressibility factor varies with temperature and pressure. In the following articles, we will study separately the effect of temperature and pressure on the compressibility curves of real gases. Effect of pressure on compressibility factor. Figure shows the variation of compressibility factor with pressure for H2N2, CO2 and CH4 at constant temperature. It is clear that very low pressures for all these gases compressibility factor is nearly equal to unity. This means that at very low pressure, the real gas exhibits nearly ideal behavior, while at high pressure, Z is always greater than unity, which indicates that gases deviate from ideal behavior at high pressure. For gases like H2 and HE, the value of Z is always more than unity, and this value shows a continuous increase as the pressure is increased. For gases like N2, O2, CH4, and CO2, the value of Z first decreases, then passes through a minimum, and increases on the pressure is increased. For carbon dioxide, the dip is larger than nitrogen, indicating that CO2 is more compressible than nitrogen. From figure, it can be predicted that whether a gas can be easily liquefied or not. The gases which show sharp decrease in the value of Z are more compressible and hence can be easily liquefied. Therefore, CO2, N2, O2, CH4 are easily liquefiable gases. Effect of temperature on compressibility factor or boil temperature. For real gases, the compressibility factor Z varies with pressure. This can be understood by comparing the plots of compressibility versus pressure of nitrogen at different temperature as shown in figure 15. Figure 15 shows the plot of compressibility factor versus pressure at different temperature. It is seen that initial dip in the curve decreases as the temperature increases. This means that the deviations from ideal behavior become less and less with increasing temperature. Ultimately, a temperature is reached where dip in the curve is minimum and that remains close to unity over an appreciable range of pressure. At this temperature, the gas behaves like an ideal gas for a particular range of pressure. Hence, Boyle's law is obeyed at this temperature. This temperature at which a real gas behaves like an ideal gas for an appreciable range of pressure is called Boyle's temperature. Now, here are again some worked examples that the students are suggested to do by their own. Now, causes of deviation from ideality. We have studied that real gases show nearly ideal behavior only at low pressure and moderately high temperature. These gases show deviation from ideal behavior at high pressure and low temperature. These results are not in accordance with the kinetic theory of gases, as the gas laws and the ideal gas equation is derived from the kinetic theory of gases, which is based upon some assumptions. Hence, the assumptions made in the kinetic theory must be modified in order to study the observed behavior of gases. In order to explain the deviation from ideality, van der Waals pointed out two faulty assumptions of kinetic theory of gases. These faulty assumptions are: the molecules are considered as point masses and the volume occupied by the gas molecules is negligible as compared to the total volume of gas. The forces of attraction between the gas molecules are negligible and the molecules move independently. These assumptions are valid only at low pressure and high temperature. Under these conditions, the volume occupied by the gas molecule is negligible as compared to the total volume of gas, but at high pressure or at low temperature the total volume of gas decreases appreciably, whereas the volume occupied by molecules remains the same because the molecules are incompressible. Therefore, the volume of the molecules of gas cannot be neglected under these conditions. Under the conditions of high pressure and low temperature, the total volume of the gas is quite small. Consequently, the distance between the molecules decreases and intermolecular forces of attraction becomes appreciable and cannot be ignored.